Hey everyone, my name is Ajay Gupta and I'm on the INTERalliance Leadership Council. INTERalliance's mission is to inspire and assist young talent to pursue an IT career in Greater Cincinnati. And if you want to join the ILC, you can go to interalliance.org to apply. The ILC runs many of the programs run by INTERalliance, mainly Tech Olympics and other programs such as this right now. Please go to interalliance.org also to join other sessions and other tech talks that are happening in the upcoming weeks. And that's about it. So I'll turn it over to you, Rachel.
Okay, thank you. So today's session is going to be kind of a blend between tech talk and also all kinds of other good stuff. In general, I'll be covering an introduction to operations research, and we'll get into a little bit more detail about what that's going to look like. So an agenda for today, I'll cover a couple different levels of introduction, specifically about me. Then we're going to learn what even is operations research, as I'm sure a lot of people have not heard the term before. We'll go through a few examples, and then hopefully I can get you interested in why operations research is important by looking at some applications in industry today. So I don't know if you guys want to do this just with this small group that we have here. Classic Cincinnati question, just so I can get to know who we're talking to today. Curious where everyone went to school. I don't know if I have the option to let you guys annotate, but if you just want to let me know. I went to Mason, so go comments. Where do you guys go to high school?
I go to Seven Hills. I'm a senior.
Okay.
I went to not Rapid Run, that's a middle school. I went to Oak Hills High School.
Okay. Cool. All right, we will move on. Okay, so just a little bit about me. My name is Rachel Hunter-Rinderle. I go to the Ohio State University. I just graduated with my bachelor's in industrial engineering this past May. So graduate in air quotes because unfortunately couldn't have a real graduation, but the diploma's on the way. And I have 1 year left working on my master's in operations research, also from Ohio State. They had a really cool opportunity to do a 5-year track to get my master's. So I've been working on my master's last year as I was finishing up my bachelor's, and then one year left. In college here at Ohio State, I've been involved in a variety of different organizations. If any of these speak to you on any level, feel free to reach out at a different time. We can talk about the organizations. I've been really involved in IISE, the Institute for Industrial and Systems Engineers, which has kind of been like my INTERalliance extension to college. They do a lot of very similar things, putting on conferences, professional networking, that type of thing. And you'll find that every major pretty much has its own professional organization. Really great to get involved with those. I was a member of Phi Sigma Rho, a social sorority for women in STEM. So really cool way to grow my network here on campus. And then also a proud mentor in College Mentors for Kids, which I can't recommend enough. The opportunity to work with kids in the area of where you go to school. So if any of those pique your interest, feel free to ask questions regarding those. My connection to INTERalliance, how did I end up here today? I was very involved in INTERalliance back in my days at Mason, and I really think that I can attribute most of my professional career up until this point to INTERalliance really helping me get started. So way back in 2014, I went to the IT Careers Camp. That was my first start. I went to the UC camp. I was on Team P&G, and I was the Chief Marketing Officer on the team. So great summer, great experience, enough to join the ILC right after camp. I was on cabinet for both years that I was in ILC. I was director of PR 2014, 2015, and then chief marketing officer 2015, 2016. The summer after I went to camp, I went back to be a student director for the Miami and Xavier camps. And then the summer after I graduated, I was an IT intern at P&G. So all around, just incredible experiences that I had with INTERalliance. Again, if anyone has any questions about how to utilize, how to really leverage your connections through INTERalliance and take as much advantage of the opportunities available as possible, you can let me know about that. I'd be happy to talk about that as well. Okay, so now we get into what authority do I have to be speaking to you about industrial applications of operations research. So as I said, I was an IT intern at Procter & Gamble through INTERalliance in 2016. The summer after, I moved out to Baltimore to be a process engineering intern with Coty, which was actually, I was at a former P&G site. Prior to 2016, Procter & Gamble owned Coty as well as about 45 other cosmetic and beauty brands that they sold to Coty. So I was essentially going out there to work for P&G, but it was under a different name. I worked in a distribution center working on safety process automation. I wore steel toes and a safety vest and safety glasses every day, getting in when the shift started at 6. So definitely an interesting experience. Loved the culture, but warehousing and wearing steel toes is not for me. So the summer after that, 2018, I spent a summer working for L Brands, which owns Victoria's Secret, Pink, and Bath & Body Works. And if you've seen any of that in the news recently, you know they're not doing so well right now, but that's okay. I took kind of a project management role there, working in their store design and construction department. The culture was very interesting. They're very laid back people, but I really learned that I was missing the technical day-to-day. I want to look at the data and I want to feel technically challenged on a daily basis. So last summer, 2019, I was finally able to get to that point. I moved out to DC to work for the Postal Service on their operations research team. I did research on batch processing and machine scheduling in their mail processing centers. So there's over 200 facilities across the country that sort mail every night. And I was working on how can we balance the mail across the machines that are available so that we can sort millions of mail pieces a night and get those out the door so that you can get your birthday cards and checks when you are expecting them. So now I'm about 4 weeks into a return to P&G as an IT intern again, but doing very, very different things. I'm in product supply data science, which product supply is P&G's fancy non-standard term for supply chain, and we will get into the details of what data science really means. So again, if anyone has any questions ever about any of the roles that I held, any of those companies that I worked for, I'd be happy to talk to anybody about all of those opportunities. I've had a lot of fun moving across the country, taking these jobs. That's really one thing I can recommend. If you get the opportunity to move, do it. So now getting into the meat of things here, of our small group here. Does anybody want to take a stab at what operations research is?
I'm pretty sure it's just researching how to optimize workplace efficiency. That's
good. I appreciate the word optimize. Good word there. Anybody else wanna jump in? If not, that's okay. No? Okay.
Yeah, I was gonna say the same thing, like something about efficiency. Oh, okay. Yeah. Kalina's asking, is it like market research?
It can be. So that's a good application, and I will put that in the back of my head and think about how I can answer that one better when we get to the application. So I will write that down. We can talk about that. So my favorite definition of operations research is that it's the science of decision making. So we're using all the data available to say or to determine what decisions make the most sense. So optimal decision making in a constrained environment, that we have limited resources, we have limited time, limited money. So deciding what's the best choice that I can make with the resources that I have available is kind of a base understanding of operations research. And Merriam-Webster defines operations research as the application of scientific and especially mathematical models to the study and analysis of problems involving complex systems. So in a nutshell, essentially we're using applied mathematics to understand the situations and the systems that we operate in to make them work better. Does anybody have any questions so far? Does that definition make sense?
When you say mathematical models, do you mean like sine, cosine, and using derivatives and integrals?
Yeah, so the goal, so I've always been a math nerd. Everything in the world can be described in terms of math, whether that's calculus terms or linear algebra terms. Everything can be described, every behavior can be described as a function. So we're taking the system, describing it as a set of functions, and then yes, we will take a lot of derivatives. I can show you a little bit about how the math part of it comes together in the example that we'll run through, but it's describing the world in math so that we can do essentially calculus to determine more answers, I guess, about the system at hand. Does that make sense?
Yeah, that makes a lot more sense.
Okay, good. So this is from Gartner, which I didn't know what Gartner was until I started with P&G this summer, but they are essentially a big consulting firm that plays a lot in the supply chain area. You hear a lot, at least I hear, and hopefully you guys hear the word analytics a lot these days, and it can mean a lot as we see. There's a wide range of what analytics can mean. So if we look at this progression here, if we start just by looking at information, we have, let's say, sales data from the last year. We can use that data to do descriptive analytics to understand what happened in the last year, but that's not super helpful moving forward. So then we can start to get into root cause analysis and other things like that to understand what factors are at play that cause that to happen. A little bit more helpful, but we still need a little bit more foresight. So we can get into what we call predictive analytics, which is we have information about the past. How can we apply that into understanding what's going to happen moving forward? So if we know the last year, on some level, we could predict what's going to happen in the next year. But we're going to see that operations research, which is one big, I guess, leg of operations research is optimization, is prescriptive analytics. How can we make it happen? How can we achieve exactly what we're after? And then just a few kind of key hot words right now that I want to point out on this spectrum. I feel like everyone's really interested in machine learning right now. Machine learning sits somewhere between diagnostic and predictive analytics, depending on what you're after. And then I'm also going to talk a lot about simulation in this presentation, and I think that simulation sits just past predictive analytics. And these are not hard settings by any means. You can use different techniques in different places, but this is kind of a base understanding of moving away from just looking at information to actually getting that information to work for us and give us the answers that we're looking for. So I'm going to walk you through a few very basic examples just so you can understand kind of the inner workings of what we're looking at, and then we'll get into some actual interesting applications to figure out why do we care about these abilities. So we're going to start with simulation. So one big arm of simulation is the Monte Carlo simulation. The term Monte Carlo is used in a lot of different ways. So you may have heard this term before. It may have been in relation to simulation, maybe not. But a really common use of Monte Carlo simulation, which uses, I'm going to use some big words here. Monte Carlo simulation uses random inputs to determine deterministic outputs. So that means we know, in a sense, what the output should be. We're going to use randomness to try to estimate that value. So we know what pi should be. You could tell me what pi equals, but we're going to use randomness to try to get a computer to give us an estimate for it. So does anybody have any ideas about what we might be doing looking at this diagram here and also looking at the two formulas or equations, whatever you want to call them, for the area of a circle and a square? Does anybody have any ideas? If not, that's okay. I can give you another hint. So what we're going to do is we're going to throw darts at this space, at this square, and we can use that information to get an estimate for pi. So we can randomly generate coordinates, x, y coordinates that fall within that square, and use a portion of those, or look at the portion of those that fall inside the circle to estimate pi. So if we want to look at this visually, here's our space that we can throw darts into, and we'll see that it doesn't matter what the radius is. I don't need to know that, but what I'm going to do is randomly generate points within that square. So in terms of, you know, running a experiment, 3 times is probably not enough times. Each of these thrown darts you could think of as an experiment. So 3 times is probably not enough. 5 times, maybe we're getting closer. But how about this? So now we are looking at, this is much better. We are looking at 31 darts fell inside the circle, 8 darts fell outside the circle, and that gives us 39 total darts. Does anybody here have an idea of what we can do with those dart numbers in a way to get an estimate for pi?
Can we substitute them in for a variable?
Yes, we will eventually. So I'm thinking in terms of ratios. Is anybody else? If not, that's okay. I think it'll make sense when I pull it up, hopefully. So are we saying this? We've got 31 darts inside the circle, 39 darts outside, or 39 darts in total, which is how many fell inside the square. And then we have the area of the circle over the area of the square. So does that ratio make sense to everybody?
So you're trying to calculate the ratio of darts inside versus outside the circle to see
versus like the area that the space takes up.
Correct. Yep. Because we know based on, so we have equations that give us area of the circle and area of the square. So we know in terms of those equations, we know a ratio, and that ratio includes pi. You also see that the r squared cancels out. So that ratio only includes pi. And then we also, after we're randomly throwing darts, we can look at the area of those spaces to be like the probability that a thrown dart falls into any given area is equal to like that area over the total. Are we following here? So if 31 out of 39 darts fell into the circle, we could say that approximately 31 over 39, whatever that is of a percent, that's how much of a percent of the area of the square that the circle takes up. I'm hoping that that's making sense. So let me show you here. So what we've done is we've canceled out, let me draw line. We can cancel our r squared. So we get 31 over 39 is equal to pi over 4. And then we can do a simple cross multiply and divide to get an estimate for pi to be 3.1794, which, as you can see, it's decently close. And if you can imagine running or throwing, so we threw 39 darts. You imagine throwing 100, 1,000, 1,000,000 darts. And by that I mean estimating 100, 1,000, or 1,000,000, or generating that many random numbers, we could get a better estimate of pi. So the concept of simulation is that we're going to use random inputs, do some kind of processing to them, and then that's going to help us understand what a representation of the real world. So I'm not agreeing that 3.1795 is equal to pi, but based on the simplification that I was able to make by generating these random numbers, it's an estimate. It's a close enough guess. So does that concept of using random inputs and a simplification of the system to get an estimate, does that make sense? Are we following?
Yeah.
I'm just wondering like how this works and like doing other stuff. Like how does this relate to operations research?
Yeah, so I'm actually going to, and I could skip ahead, but I'm going to run through a base example of optimization, and then we'll come back to applications of simulation in the real world. So Monte Carlo simulations are really, I mean, at least this form of a Monte Carlo simulation, we don't need something to tell us what pi might equal. We know what pi equals. We are far beyond needing a Monte Carlo estimate of pi in our daily lives, obviously. But this just really helps to show we've randomly generated inputs and we're going to get an answer on the other end. And I'll show you some examples of more interesting applicable reasons we would want to generate random inputs to get an output. For a quick example here, one that we always go back to in classes is, let's pretend you've got one ice cream truck parked at the park, and there's one ice cream server inside that ice cream truck. So we would call that an MM1Q. That just means that there's one server. The service time, so the amount of time that you spend standing at the window from the time that you walk up to the window to the time that you walk away with your ice cream, service times are exponentially distributed. So we're talking about these random number generations. If you can think about an exponential curve, you know, the asymptote like at 0 and that, you know what I'm talking about.
Yeah.
Or I can draw it. Okay, so essentially, service times being exponentially distributed means that we're going to pick a random number from an exponential distribution. So instead of a normal distribution where you're most likely to pick 0 and you might pick -1, you might pick 1, exponential distribution, you're most likely to pick the lower numbers, but you may pick a big number. So if you can think of an exponential probability distribution. And then we're also saying that in our arrival time, so the time between one person and then the next person showing up at the ice cream truck occur according to a Poisson process. There's a lot there. Basically, we're just saying there are assumptions we can make about the rates at which people are going to arrive to this ice cream truck. So what we can do is, based on our understanding of these probability distributions of how long or how often people show up and how long it takes them to get their ice cream, we could model that over an hour, 4 hours, a whole day. And at the end of that modeling, we could say, on average, how long do people spend waiting in line? How often is the server busy? How often is the server not busy? How on average at any given time, how many people are waiting in line. And then we can use that information to answer questions like, should we add another server? Are there changes to the queuing or the line process that we can make? So that might be a little bit more of like a clear extension, like that can show you how that can be applicable in real life. Obviously, no one's using simulation to estimate pi, but this emphasizes that we're using random inputs to get answers about simplifications of the real world. Does that application make sense with just me using words and not having anything to show you on that?
Yeah, I understand it from a business model.
Yep.
So can it be applied to things other than business?
All kinds of things. So financials use simulation a lot. So thinking about how many moves and at what rates, those are simulations. Simulations can be used everywhere. Even like a flight simulator has the word simulator in it, where we're looking at a simplification of the real world to gain an understanding about how things might react when they are in the real world. I think that's a good base understanding of simulation, is that we're making assumptions, but we're going to try to test the system without making changes to the real world. So in general, we're building a model that simplifies the real world, but still allows us to make conclusions about how things operate within that system.
Cool.
Is that I will definitely admit, if we could split operations research into two things, we've got modeling or optimization and simulation. And my personal favorite between those two is definitely modeling and optimization. So I am no way an expert on simulation, and I can look for other resources to point you towards. But I hopefully can answer more questions from an optimization perspective. So I'm going to, oh, I don't know how to get rid of my annotations. Let me clear all. Okay. So I'm going to move into a basic example of optimization, and then we'll come back to some more applications, and we can brainstorm a little bit more where we might see each of these things. So why is this doing? Okay. So a very basic word problem here. We have a bike production facility that makes two types of bikes, mountain bikes and street bikes. Up to 2 mountain bikes can be made per day, and each brings in a $15 profit. And then up to 3 street bikes can be made per day at a profit of $10 per bike. Both bike types use the same machines, so only 4 total bikes can be made per day. All bikes produced are sold the same day, so we're not restricted in any way by how much we can sell, it's just how much we can make. So we're going to ask, how many of each bike type should the facility produce to be able to maximize their profit? So first, I'm going to ask, I remember very basic problems of this sort coming up in, I think, Algebra 2 when I was in high school. Does this type of problem stand out to anybody? Has anybody seen a problem like this before?
Yeah.
If not, that's totally fine.
Yeah,
you have seen these?
Yeah.
Okay. Okay, so I will hopefully not bore you, but this is the most basic form of an optimization problem that you could see. So let me point out here, we have our constraints, which are the parts of the problem that are going to restrict our choices, restrict the options that we might want to make. So that's that only 2 mountain bikes, 3 street bikes, and 4 total bikes can be made per day. We've got problem data. This is that there's $15 profit per mountain bike and $10 profit per street bike. We have a decision or multiple decisions to be made. This is how many of each bike type should we be making. And then we also have an objective. Here we're looking to maximize profit. You've got 2 options for your objective. You could either maximize something or minimize something. So you could think about maximizing profit or minimizing cost. Those are the 2 most common objectives, but it could be anything really. And that's part of the fun part, is that it could be anything. So what we're going to do is write this in math terms, and hopefully the color coding can help you make the connections here. So we are maximizing profit. This, as I said before, what we're trying to do is define our system in terms of math so that we can do calculus. So this is how we're going to define profit. We know that we can make, or that our profit would be equal to 15 times the number of mountain bikes that we make plus 10 times the number of street bikes that we make. This here in green is showing that mountain and street are the 2 variables that we're trying to decide. So we haven't yet set a value on either of those. Those can change, and those changes are what's going to change our objective function value, which we're trying to maximize here. But we know that we can't make any changes that we want. We have these constraints here. ST stands for subject to. So we want to maximize the value we can get out of 15 times mountain plus 10 times street, bearing in mind that mountain has to be less than or equal to 2, street has to be less than or equal to 3, and the 2 together have to be less than or equal to 4. And then this down here, if no one has seen this symbol before, this is saying positive integers. So we can't make half of a bike. We also can't make negative bikes. So this is just saying that when we decide on a value for mountain and street, they need to both be positive and they need to both be integer values. So does this, getting from the word problem to the math, does that make sense to people? Are we following how we made those equations?
Yeah.
Okay.
That's a lot of variables.
So there's only two. So mountain and street are the only two variables, but yes, we need a bunch of equations, and those variables need to exist in a bunch of different ways to fully define the system. So all of the interactions between mountain and street, or the number of each type of bike that you make, need to be defined for the problem to be considered well defined. So how do they interact to equal a profit? Each one is individually constrained, the two together are constrained, but at the end of the day, we need to decide how many mountain bikes and how many street bikes. And these, I will say that this is a very simple example. I'll just jump in right here to say that the research that I was doing with the Postal Service last summer, there were hundreds of thousands of constraints. We've got 3 constraints. I was working on a problem that had hundreds of thousands of constraints and millions of decision variables. So if you're worried about how computer science comes into the operations research world, it's that we've got problems that are huge, and without some understanding of computer science, would never solve on the types of laptops that we have. We're looking at problems that still take days to solve. You right now type something into your calculator or into Excel, you have an answer in an instant. We're looking at solving math problems that still take a computer days to solve, which I think is really cool because it's stuff that a human could never figure out. So this is a simple problem, so we can solve it graphically, and I'm going to walk you through that just so you can see what's going on here. So what I've graphed here in green is called the feasible region. The feasible region is where all of the constraints that we've set out overlap. It's where all of these are true. So we said that mountain had, I've got a coordinate system here where mountain is kind of like the X variable and street is kind of like Y. So I've said mountain needs to be less than or equal to 2. Okay, I'm only going to look over here. Street needs to be less than or equal to 3. Okay, I can only look down here. So at that point, we're in this rectangle. But we also know that mountain plus street needs to be less than or equal to 4, which is this. And they all need to be greater than 0. So we're looking in this green region is what all of our options could be. The feasible region is where those combinations of decision variable values are considered feasible. They work with the constraints. And what we're going to consider the optimal solution, or the answer that we want to go with, is the feasible point, the allowable point, with the greatest objective function value. So if these are all of my options, where in this feasible region can I maximize my objective function value? Where can I maximize the profit, which is exactly what I said I was after in the problem. So what we're going to do is plot the objective function for increasing values. So we're essentially plotting like a contour plot, which hopefully hopefully we're following here. So this first red line shows any combination. If you can think of any XY point along this line, well, it's going to have the same profit value of 20. So you could pick the point right here, whatever that is. Let's pretend for a second you could make half of a bike. So 1.5 mountain bikes and 0 street bikes is going to give us a profit of 20, all the way up here to 2 street bikes and 0 mountain bikes is also going to give us a profit of 20. We could draw a similar line for 30, 40, and what we can see is that the objective function is increasing in the direction of that red dotted arrow. And because it's a linear function, we know that it will always be increasing in that direction. I hope I haven't lost you, but if I have, please let me know. Are we following, like, the red stands alone from the green for right now? We're just looking at our objective function, which is the representation of the profit, and trying to figure out how it would increase across the solution space. Does that concept make sense?
So, oh, you can go first.
Okay, so where the line crosses is where you get the most profit.
So So we're going to get the most profit this red circle right here. So the right intuition, yes. But what we're saying is that in the arrow across the whole space, in the direction of this arrow is how we're increasing our objective function value. And if you can think kind of at an angle here, the furthest we can move in this direction is actually out here at this point. There's no, if you continued to draw these red lines in this direction, your highest one would hit at that point. Does that make sense?
Mm-hmm. Yeah.
Okay, and then Ajay, did you have,
Yeah.
or was that your question?
No, my question was for like finding the red lines. Let's say like you're doing this with like tons of variables. Do you like so like would you use like computer science to like make the red lines come automatically, like program it, or do you like manually like calculate where each red line goes?
No, so this is a very, very simple example, and the examples do not have to get very complex before figuring out where the red lines hit would be difficult. If you could even think of an objective function that's nonlinear, so let's say we have something squared or something to the third power in, or anything else, and the objective function value, drawing, this would be called a contour plot, where you're just graphing like those equal values. That can get really nasty really fast. So you would, I'll say, never actually solve one of these problems by hand. I just wanted to show you intuitively in a very, very simple example the kind of concepts that we're looking for. So if you can picture the profit as being the z axis or the z variable coming out of the page towards you, can anybody picture the red lines as making a plane that sits at an angle and rises in the direction of the red arrow? Can we picture that, or is that too difficult to picture in 2D? Because if you could picture a plane, it's a plane because it's linear. It's just a sheet of paper, and it's going to increase in the direction of that red arrow. Essentially, you would cut that plane to only be looking at the feasible region projection of it, the parts of it that fall within the feasible region, and the highest point on that plane would be at the red circle. But as soon as that starts to bend and no longer be a plane, but it's a mess of who knows what, it's impossible to visualize, and you just have to use programming. And I have two formulations here. You can do these types of things up to a certain point in Excel, and then there's also just some programming that you can do, and I have two of those formulations on here as well. So we can see that our highest objective function value we can achieve is at the 0.22, which we would consider the optimal solution. So our answer to the original question of the problem is that the facility should produce 2 mountain bikes and 2 street bikes per day for a total daily profit of $50. So like I was just saying, for the most interesting problems, and for really any interesting problem, this is going to be far too complex to solve by hand. So we use software to do this. Here's one example which you guys can totally mess around with. Excel Solver is a free add-in on Microsoft Excel. If you've never used it, I definitely recommend playing around with it. But here I have it set up. This is my data. So I know that it's $15 and $10 profit each. These are my constraints. I can make 2, 3, and 4 total. These cells right here were left blank for the optimizer to the side. And then this was also, actually this was not left blank. Cell E4, you put your formula in for your objective function. So actually E4 is equal to this cell times that profit plus this cell times that profit. So you go into Excel Solver, you say, this cell right here is my objective function, and I want you to change these cells to maximize what ends up coming from that formula in this cell. And then we can see here, these are all the constraints that I've set. They're the same as they were before. We need our decisions to be integer. We need them to be greater than 0. and then this is the total production, street bike and mountain bike. And so you're just kind of like building the relationships between the cells in the same way that you originally mathematically wrote out the constraints. So does the concept of this make sense? Excel uses, you can select your solving method. Excel uses simplex, which is the most common algorithm that you would use to solve a linear program. And if you take a linear programming class, you would learn how to do the simplex method by hand. It's a lot of matrices and linear algebra. So if you thought in high school that you hated matrices like I thought I did, you may learn to love them, or you may still hate them. I don't know. But it's a lot of linear algebra, like matrix multiplication and that kind of thing. But that's how a computer would solve the problem. I thought that was far too confusing to try to explain today. But essentially, yep, what's up?
How long would a computer take to calculate this?
So something like this is going to happen essentially instantly. Maybe 1 to 2 seconds max, probably not even for a computer to solve something this simple. But like I said, and it's not uncommon for your decision variables and constraint counts to reach hundreds of thousands and millions, and that's when you get into problems that take a couple of days to solve. And I would never put something that complicated in Excel. I haven't really experimented with Excel's limits in this regard, but I would only do small to mid-sized problems in Excel. And then I'll go to the next slide here. So GAMS is also limited in the number of constraints and decision variables that you can use, but the syntax of it reminds me more of what you would use in industry, which you could be using Python, or all kinds of different languages have the ability to do optimization. But this is kind of more of a classic, like if you feel like you're programming way to do this. And again, this would happen in less than a second, but we've just defined our variables. This right here is like our what we want to call our objective function. GAMS, general algebraic modeling system, is what we used in school. It's kind of funky. Some of these things are just how GAMS is, but we're saying that our objective function, which is profit, is equal to 15 times mountain plus 10 times street. Mountain is less than or equal to 2, street is less than or equal to 3, mountain plus street is less than or equal to 4. I've named the model bikes. I want to use all of the constraints. I'm going to solve it using mixed integer programming, which just means that you can't call it linear programming anymore when your variables have to be integers. It's mixed integer programming at that point, and then we're maximizing profit. So it says the same thing, just in like GAMS syntax. And then this is an example of what a part of the output would look like. This is telling us that the answer or the decision for mountain is 2, the decision for street is 2, and the profit is 50. So we can see that we got the same answer doing the problem by hand, solving it in Excel, and also solving it in GAMS. And I will go back, bear with me for a second as I bounce back through all of this. What I want to suggest for a second, and we'll get into this because the only slides I have left are kind of brainstorming applications or why any of this would be useful. Looking at a problem like this, I want you to think for a second, what if instead of this simple problem, we considered our constraints to be the road network that's available, speed limits, road closures, which roads are one way, that type of thing. Data, actually, I guess our speed limits would be considered data, and that would probably be one of the only things in data. Let's say that the decisions we wanted to consider were which turns should I make when, which roads should I take at which point, and our objective could be minimize total distance traveled, minimize time. We could also consider data to be point A and point B. What have I just described? If we're going to decide when to turn where, and we want to minimize time from point A to point B. anyone picking up what I'm putting down there?
Sorry, could you repeat it one more time?
Yeah, so looking at constraints, data, decisions, and objectives as the 4 building blocks of an optimization model, if instead of this very simple bike example, we wanted to consider an objective of minimized time that it takes to get from point A to point B, and we wanted to consider the decisions of which turns should I take when, which roads should I travel on. The data we wanted to include would be something like speed limits, and the constraints would be that you could only drive on pre-existing roads in the correct direction. What common tool that we use all the time would that give us?
Navigation.
Yeah, so that is a GPS. Every time you type in a location that you want to go to on your GPS and hit go, and it might take 5 seconds or so for it to give you an answer of what route you should take and how long it's going to take you to get there. That is an optimization model. That's called, we call it a shortest path problem, aptly named. We want to take the shortest path to get to our final destination. And if you think about all of the options that you have to get anywhere that you want to go, even if you're going a couple blocks away, do I turn here or do I turn at the next one? Should I go around the block 6 times and then come back? There are so many decisions that have to be made, and the GPS can solve that for you in a couple of seconds. So that's where the computer science aspect comes in. You have to understand your problem well enough. You have to take advantage of problem characteristics to reduce your solution space, all that kind of stuff. But that's just one simple example of what the constraints and decision and objective might look like in something that we use every day. That I'm sure people, hit go on Apple or Google Maps all the time and don't think about what's happening kind of under the hood there. So, okay, bear with me as I pop back through. Does that application of optimization make sense? And does anybody have any questions about that or anything else so far?
So when you're trying to optimize something, do you use multiple models to prove one point like we just did, or do you choose one model and just go for it and hope you get a good?
So do you mean how we solved the bike one like by hand and then in Excel and then I showed you the GAMs? Is that what you're?
Yeah, that's what I'm referring to. So in the real world, would you use multiple methods to solve one problem? Or would you just say, we're going to stick with graphing and try to figure it out?
So, yeah, I think I lost you for a second because unfortunately Columbus sent us a nice public safety alert. But I think I picked up on what you're saying, and if not, correct me. You would not, I was trying to show different ways to arrive at the same solution, hopefully in increasing terms of like complexity, if that makes sense. You would not in any situation have to say, okay, I've graphed it, now let me solve it in Excel, now let me solve it in GAMS, because as you saw, we got the same answer every time. There are plenty of situations where you would want to start with some sort of graphical understanding because you need to know on some level some kind of visualization of what your problem looks like to be able to even start solving it. We looked at a fully linear example. Every equation in that formulation was linear. When you start looking at nonlinear problems, so let's picture, for example, x squared. Who knows what x is? But let's say your objective function that you're trying to maximize is x squared. I couldn't even think off the top of my head what you might want to maximize in its squared value. But let's just say that. And let's also say that our x value that we want to choose is not restricted. We could choose +2 just as easily as we could choose -2. So if you put that in a computer, the computer is going to be confused because it doesn't know, well, we could maximize going in the negative direction or going in the positive direction. I don't know which direction you want me to go. So you, in that situation, would want to start with graphing to get a little bit of understanding, okay, where might a solver have a problem in solving this problem? So there are still situations where human intuition is valuable to the computer before it starts solving. But again, you will get to points where you could not graph it if you wanted to. So there are other ways to start thinking about how can I take some time to understand what's the structure of my problem, what does it look like without actually having to look at it, to help your solver along the way. But then at the end of the day, so I'm using Python this summer. I picked Python. I'm gonna write my model in Python. I'm gonna run it. I need to assess the solution. I need to say, does this make any sense? But I don't need to also go and run it. I don't need to graph the final solution to be able to hand it off to my manager. Does that make sense?
Yeah. Okay, thank you. Yeah.
Cool. So some more applications. Has anybody, and I've got my short list of simulation applications, but before I show my list, does anybody have any thoughts of where, that we haven't discussed yet, of where simulation might be helpful in the real world? If not, that's fine. I can jump through mine. I'll pull this one up. Definitely relevant. Has anybody seen any articles that include, hopefully they're actually calling them simulations, but information about coronavirus, and saying, I saw a lot when the social and physical distancing recommendations started to come out, little graphics showing how disease transmission changes based on implementing, the 6-foot rule or the groupings of no larger than 10 rule, and showing like, here's what it would be if we went about our lives in a normal way, and here's what disease transmission could look like if we implemented these measures. I'd hope that some of you guys had seen those, and if not, I can provide links for some of the ones that I think are really cool. That's simulation. That's saying I have a basic understanding of how the world works, and instead of trying to change the real world, because we don't really have time to test, I have an idea. What if maybe we stayed 6 feet apart? Okay, now let's go try that. How long do we have to do that before we have enough data to be able to make conclusions about any changes that occurred? We don't have enough time to do that. So simulation allows us to change the world without actually having to change the real world, take risks. We don't know if that's going to make things better or worse, and also take the time to do that. So disease transmission is a very common use of, or application, I guess, of simulation, and hopefully is getting a little bit more attention in these times of trying to make quick decisions. As far as policies moving forward, that's all simulation. Hospital waiting rooms, or really any type of waiting room, any type of queuing system. I've done analyses of the line waiting for security at the airport. There's a whole branch of study called queuing theory, which is literally just analyzing how we wait in lines. It's very interesting. You would think that it's boring because waiting in lines is boring, but it's all about how to make lines move faster. And also there's a little bit of a psychological effect there. You'll see that almost every airport security line that you wait in, the lines are in an S-curve shape, and that's because there's data to support the fact that people feel like they're moving through lines faster when they're in an S shape. Whether the line's moving faster or not, it makes people feel better about the fact that they're waiting in line. They think they're making more progress. So any place that you're going to see a long line like that is going to be in an S shape to hopefully help with a little bit of the mentality. But we can model in a situation, patients come in, they're essentially triaged, they could wait for who knows how long, then they could get admitted. I don't know all the inner workings of the process of getting admitted in the hospital, but we can model that so that we could say, what if we added another person at the front desk? What if we added another triage station? Like which changes could we make to seriously improve the amount of time that people spend in the waiting room. And you might run it through the simulation, realize that it's really not going to make that much of a difference, and you've saved yourself money of either hiring another person to work at the front desk, building another triage station, building a whole other wing. These are things that we can essentially run. You could think of it as a virtual experiment before you have to actually go out and do the real thing. And it's all statistics. If you like statistics, you'll like simulation. It is 100% statistics. And then a little bit closer to home for me, you can use simulation to think about manufacturing line design. So all the way from physical placement in a plant of where does it make sense to put this product making line and product packing line to then get it to the racks that we're going to store it in, all the way to simulating line speeds. So if I have the beginning portion of my line running at this speed, and then we switch to a different phase of the line, we can run it at a different speed. We can optimize the whole line through simulating different portions of the line running at different speeds and getting feed from different areas. Do those examples make sense? Do they spark any other ideas with people? Does anybody have any questions? So as far as optimization is concerned, have any other applications or ideas of how optimization works in the real world come to anybody's mind? If not, I can run through my list of things. But if you have any ideas, shout them out, feel free.
Manufacturing?
Yeah, so all of this is applicable to manufacturing. We already talked about the GPS example. Scheduling, optimization, operations research is widely applicable to scheduling all the way from, I talked about, I was doing machine scheduling at the Postal Service, saying at what times should what machines run what mail or what products, all the way to you can do facility or employee scheduling. One example that sticks out in my head is like nurse scheduling at a hospital. Like, you know how many hours everybody in total can work in a week. You know how many hours everybody can work in a row. You know how many hours they have to have a break in between shifts. Like, you have to be home for 8 hours before you can come back. You know who's qualified to do what jobs. You know at any given time how many nurses you need to have on staff. That's a big optimization problem, and other things like that. Revenue management. Has anybody ever noticed that if you get on to buy a plane ticket, those prices change all the time? That's revenue management. Those are optimization models that are built on some probabilistic or like statistical understanding of at any given time, both based on the time that you're buying your ticket, how far in advance, and actual time of day, and time of day of the flight. How likely are people to not show up because you know that airlines are overbooking every flight that they sell? How likely are you to switch your flight, to ask for a refund? A lot of that is based on business versus leisure travel, certain things like that. So the fact that a flight price could change minute by minute is optimization, specifically called revenue management. Neural networks. I'm not even going to pretend that I really have an understanding of how neural nets work, but I do know that it is optimization. So that's a little bit closer to a computer science application for people that are really stuck on programming, which I can't agree with because I enjoyed programming but could not see myself doing it forever. Vehicle routing. So this is really applicable to delivery services. How does Amazon, Postal Service, UPS decide in what order they want to deliver your packages? That's all optimization. And then also inventory theory, which is exactly what I'm doing this summer. We've got mixed centers across the country that hold all the products that P&G sells, and I'm building a model to determine at any given time how much of each product should we hold in each mixed center so that we can deliver on time to the customers when they want it. So there's a lot of, we have to understand or pretend to understand what forecasts are going to be coming in when, and we're space constrained. There's really not enough space in each of these mixed centers to hold everything that we would want to, but taking demand volatility into account, and there's a lot of unknowns. How can we optimize, which my objective function is looking to be, how do we minimize service loss? So how do I minimize the number of cases of product that a customer wants that I don't get to send? That would be a service loss. How do I minimize that, taking all the rest of those things into account? So inventory theory, you could take classes on classes on classes of how much product should you hold, how much product should you make, how often should you make product, where should you store your product, all that kind of stuff is all optimization. Does anybody have any questions about any of those?
So if I wanted to practice this at home, I could just get like a button making kit and just practice collecting data to see if I can move faster through that sort of thing? Because
Possibly.
I really
I will look into resources to get started with simulation at home, and I can get back to you on that. I can send it, and then I guess you could send out to anybody who might be interested. I can work on getting some resources together for anybody who would be interested in kind of playing with this stuff at home. I would say that simulation is one of the harder things to just kind of like get into on your own, because usually the software that you need to do so and the data that you would need to do so is just, it's not necessarily the stuff that you can just make up on your own, if that makes sense. Like, you would need real data, but I will definitely do some research and see, and I can also compile just like interesting resources. I'll get some links together about the coronavirus modeling for anybody who's interested in reading about that. Any other questions on simulation? Like I said, I am no simulation expert, but I find it really interesting.
Did you get into this in high school? Because I
did not.
Okay.
So I actually, it's kind of a cool story. I know we're 5 o'clock, so I will not hold anybody too late, but I had made it to my sophomore year of college. I came into Ohio State as an industrial engineering major. I don't really know why I thought I wanted to be an IE, but I knew that somehow. And I was about ready to change my major to computer science because something just wasn't feeling quite right. And then one of the OR faculty came into one of my classes, did a session similar to this, saying, this is what operations research is. You can focus on it here in the industrial engineering department. And I remember thinking, wow, a week ago I was ready to change my major, but this is everything I've ever wanted to do. And I really didn't learn about simulation until this past fall, because you have to have a really solid statistics and experimental design background to really get into the nitty-gritty of simulation. So it doesn't come up until later in the IE curriculum at Ohio State. So no, I did not know about it in high school. I didn't know about it until recently, but it's happening all around us. It's very applicable, and it's some pretty cool stuff.
Do you have sorry, I was going to say, do you have any tips for anyone wanting to go into this? I'm thinking about it now because it sounds really interesting. Yeah, so I would say that the biggest application, or I guess like the biggest connection from simulation to academia is in industrial engineering. I can't think of anywhere. I mean, like, mechanical engineers would do like material simulation. Like, if I bend a rod, what's going to happen to it? At what point is it going to break? That's also simulation. I don't find that stuff very interesting because I'm not interested in like materials. If simulation and statistics and optimization are things that you're interested in, then I'd be looking at industrial engineering and operations research as career fields and academic paths. Like I said, I will try to get some resources together for like what you can do from an exploratory perspective at home on your own. But as far as really wanting to study simulation, I can't recommend anything more than an industrial engineering program. Thank you. Yeah. So that's all I had as far as slides, and I know that I wrote down at the beginning the note about market research. So I can speak to that, not in very much detail, but from what I know. And I'll give a P&G example because that's kind of where my head is right now.
P&G, well, I'll start by saying you'll see optimization in supply chain applications a lot more than anything, or at a place like P&G, and supply chain a lot more than anything else, because we have good supply chain data. You need data to be able to do optimization or simulation. We have a lot more solid data and understanding in supply chain. But in marketing, there are models being built that can tell you, where would my ad dollars be best spent? How much money should I spend on ads on live TV versus ads on Hulu? How do I know who I should be targeting with what ads? All of those types of things can be optimization models. I don't see as much of an application of simulation in marketing or market research, but the ad spending, and then also being able to track the impact that your ads have made, and then like bring that back into your models to be able to improve moving forward. Definitely growing applications of optimization. It all rests on good data, which it's just a lot harder to get solid data from a market perspective. But yes, it's a growing field. So we would call that like commercial or neighborhood analytics, trying to understand better the data about our consumers is definitely a goal. So with that, if anybody has any further questions about anything that I mentioned today, feel free to ask. My name and my email are at the bottom of the slide there. If you have any questions at any point, feel free to email me. You can also add me on LinkedIn. I'm like kind of active on LinkedIn, kind of not. But definitely reach out, even like the intro stuff that I covered at the beginning about school or past experiences that I've had. I'd be happy to talk to anybody about any of that. So
I guess that's it. Thank you so much again.
okay.
Yeah,
Yeah,
thank you so much,
thank
Rachel,
you,
for
guys.
coming. Thank you, everyone. Well, it's only 5 of us, so thanks for just sticking through all this. This was
Yeah.
really informational. Can't wait to see this go up on YouTube.
Yeah,
I
I'm
will
really glad I
recommend-
learned about this. I had no idea what this was, and now it's like, honestly, I'm considering this.